Good morning. I am pinch hitting for Camille Mamet, who unfortunately could not be here today, and so I hope I do her justice to her slides. So I'll be talking about some work that arose out of our research into meta-analysis for fMRI. So, as you probably know, that when you have multiple subjects, when you have multiple subjects, you have to combine them in some way, and you do that by taking, ideally, both the mean estimate and the standard error estimate, or sometimes called in FSL the COPE and the VAR COPE, and you bring that into a group level. And it turns out that the optimal way to combine group results into a meta-analysis result is actually done in the exact symmetric way. You take the COPE and the VAR COPE estimates from individual studies and you combine them, giving you a meta-analysis result where you both get parameter estimates of what is the group estimate, the meta-level estimate and the meta-level standard error, giving you the best possible estimates of the population effect and its uncertainty. So how do we do this? What are the actual machinery behind this? Well, it's just the good old-fashioned general linear model, but it is a variance components model. There are two different components of variance that we have to pay attention to. So if these are the vector responses for each study, it's the Y. We have some design matrix, so this could be what is sometimes called a meta-regression, explaining differences between studies. Typically, though, X is just a column of ones, just saying we want to know what is the average across subjects, across studies, and a beta estimate. And the variance is not just a single parameter, it's a between study variance, and then a within study variance, which in the standard group level fMRI is between subject and the variance at the subject level. Now the good thing is that usually within a subject, we have lots of data to estimate this sigma squared I. But at the study level, if we're doing a meta-analysis, we only may have 20 subjects. So instead of having hundreds of scans to estimate this, now we only have, say, 20 subjects to estimate what is the within study variance, and then be able to estimate the between study variance and tau squared. So how do we get these estimates? Well, there are two different approaches that we can use. We could use just a regular ordinary least squares approach. This is the standard approach that's used in SPM for combining subjects together. What is that estimate? Well, in the simplest case where that X is just a column of ones, the actual estimate is just the sum. Now, it's a little bit weird here because normally we take the average of the Y's, but in fact, we have to standardize this not by n, but root n, so we get something that has a variance that's just between subject or between study variance. And this thing, if we have normality, is just, will follow a t-distribution, accounting for the uncertainty in this sigma squared c. And what I sort of forgotten, I certainly knew this at some point, but I just never really appreciated, is that it's a slightly different case if we're trying to use the fact that we don't have homogeneous variance. There's both a between study variance and a within study variance. We're not really doing ordinary least squares. We're doing something what I would probably call feasible least squares, feasible generalized least squares. If I knew these two parameters exactly, I could say this is generalized least squares. But in fact, I have to plug in estimates of these tau squareds in this sigma I squared, and so hence we're calling it a feasible least squared. I have to say the echo in this room is profound. It's very surreal. So what is that? Well, that's a weighting factor, and these weights are determined by this. And again, if there were no hats here, we could just call this generalized least squares. But there are hats, so we have to call this feasible least squares. And this is the thing I often forget, that actually this is only approximately t-distribution. Why? Because again, this is not the true tau hat, it's an estimate of the tau hat. So what are the options? Well, if you were to do this option here, this is just a one-sample t-test in SPM, or a mixed effects simple OLS in FSL, which is generally not recommended, or a 3D t-test in AFNI. if you actually want to do this, where you account for both the within and the between study variance, you'd have to use SPM's mixed effects model, which is implemented. It's there. It's a little known feature of SPM. But this is the default way that we combine subjects in FSL, and you can use that same method to combine studies. And if AFNI has a similar tool to use both the within the estimates and the standard errors, this one called 3D MIMA. So basically, the foundation of this talk is a bunch of simulations that we did initially in meta-analysis, and then we repurposed them for group fMRI analyses, and they all have an outcome that looks like this. We're going to conduct a lot of p-values under the null hypothesis. So in fact, there's no true effect, and we are going to compare those p-values to what we expect by chance. So we're going to plot them at basically what's kind of like a Bland-Altman plot, but it's not quite. We're going to show just the expected. I guess it's a type of instead of a PP plot, it's a difference PP plot. It's inspired by Bland-Altman. We'll have just the true expected p-values, which we're doing. We can get them because we're using Monte Carlo, and the difference of the log p-values on the y-axis. So we have ways of computing the standard errors, so we'll show that in gray. And if we have patterns like this is telling us that our method is actually invalid. The p-values are too significant. And if they go down here, they're actually conservative. They're not as powerful as they could be. And if they fall within the gray boundary, then we have evidence that we have a consistent and exact test. So what's kicked off this work was some simulations that we did initially from meta-analysis. So let me explain the setting here. So if we just fix the between study variance to have some common value, say 1, then I can consider a range of homogeneous variance for the within study variance. And that varies to being 1/4 of the between study variance, or actually being 4 times the value of the within study variance. And if you look carefully at these colors, you'll see that these colors always fall below the line. So the impact of having a range of different within study variances actually tends to make the results conservative. And it doesn't really matter whether you have 20 subjects or 100 subjects, they're both conservative. However, if you have heterogeneity, so actually if you have a range of variance, of different variances in a group of studies you're trying to combine, as illustrated here, you actually see that these are actually inflated. So this is showing that the sort of should be the best practice way to combine studies lead to increased variance, and only gets better when you have 50 subjects. So in some ways, we should not have been surprised about this because it's an asymptotic method. The way that we combine studies where we have to estimate the between study variance is only valid for large samples. So it didn't matter that I've got some studies with 100 subjects in them. What matters was how many studies I was combining. So this was pretty startling for us because we realized, actually, wait a minute, the methods that we use to combine studies are the very same methods that we use to combine subjects in first level fMRI. So we turned this to say, is this going to affect group level fMRI? So we are very grateful to Irene Tracy, who has, over the years, collected a large number of pain studies, and she's let us combine these for our meta-analysis work. They are indeed actually all from the same lab. They're all about pain, but they actually comprise a heterogeneous group of studies. Some of them are thermal pain, some of them are mechanical pain. They're different manipulations, but they comprise a group of studies all from the same lab. They're investigating pain. So they have a range in number of subjects, and they have a range in number of variances, and we have some arbitrary ways we can look at box plots to try to get some sense of how many outliers there are. We use those settings to configure a simulation so we know that we have representative parameters in our analysis. So what do? We started with 2 different setups where we have 25 and 50 subjects, where we set the between subject variance to be 1, and then we have the mean within subject variance to be 1, and we're going to consider a range of heterogeneity, because that's what we're worried about. We saw that in the meta-analysis setting, that heterogeneity of the within their study, and now I'm worried about within subject variance, varying. So what is this like? This is a case where you either had a range of number of scan lengths within subjects, or, as is often the case, a range of quality. You have some subjects that are really good, they have very small variance, some subjects are not so good, they have high variance. And again, if you're using SPM, you probably wouldn't worry about that because you're not actually taking forward the within subject variance. But if we do things what should be the optimal way, for example, in using a mixed effects approach, this does matter. So we're going to consider a range of the worst, that is the max within subject variance, to the min of either the equal or as up to factor of 10. And then we'll also look at the impact of having outliers, either being a quarter or up to meaning about 16% will be outliers, but the impact of those outliers are to be very small, having variances that are too small or too large. Now, this may seem weird, but it is actually kind of an outlier to have very small variance. And this would correspond to having, say, a subject that had 4 times as many scans is going to give you something that has a variance that's a quarter of all the rest of the subjects. So it's both kind of small outliers and big outliers. We use lots of realizations. And so I'm showing you on the bottom, this is the feasible generalized least squares. So this is the results from using what should be the best practice method, where we estimate the between subject variance. This is exactly what's going on in 3D MIMA or FSL's mixed effects combining, which again is the default, or in the mixed effects module of SPM. And what you see is that for when the between study heterogeneity, when the heterogeneity is large, we actually get invalid tests. These are actually valid here, these are conservative. And it varies and only picks up and gets valid when we have lots of subjects. Again, in some ways not surprising, this is what we saw in the meta-analysis setting, and what we have is it's only when we have 50 subjects does it work. Now, down the bottom, is not the optimal way to combine these studies. This is using equal weighting across a range of subjects. But the one thing we can say about it is it is valid if we just use ordinary least squares. And then if we add outliers onto that, we still have some trouble in the feasible least squares. And then if we go back to the actual data, because we had the actual real meta-analysis data from the Tracy study, we can compare how different are the feasible least squares and the within, and there actually is some considerable difference between these. Okay, so the conclusions is that to our surprise, but although somehow we should have known this, that the method we're using for feasible generalized least squares can be invalid in small samples depending on the heterogeneity of the studies. Again, depending on whether there's lots of strong heteroscedasticity, variation in the variance, or some low variance outliers. So actually, the low variance outliers can control the trouble. It can be the trouble, but the simple unweighted least squares method is valid if it is not entirely optimal. I'll stop there. Thanks.